Okay, so let's continue. So we have talked about block codes and systematic block codes, and now we have talked about what errors can occur and how to model that. And the basic equation is that the output bits is equal to the input bits to the channel plus an error pattern, where the plus here is modulo 2 addition. And the error pattern determines where the error occurs, position-wise. And if we count the number of ones in the error pattern, we count the number of errors that have occurred for that particular code word. Okay? And then, as we transmit code words, these changes from time to time, obviously, right? Because the noise changes from time to time. Sometimes there are no errors, and sometimes there are errors. There could be one single error, or it could be up to n errors, where n is the number of bits in the code word. All right, so error detection, how does that work? The principle is very simple. We know that the code word, the bits that we transmit, is a member of the code. Okay? It can only be this pattern, this pattern, this pattern, and this pattern. The receiver, looking at y, can then say, is y one of these patterns? If it is, it says, okay, seems okay. If y is not one of these patterns, the receiver can be sure that an error has occurred. Right? So I'll take that again because this is a super important principle, even though, okay. So we know that one of these have been transmitted, and if the receive pattern is 0, 0, 0, say, then the receiver simply looks at this pattern and see, can I find it here in the code? And says, yes, I could. So this is a member of the code, and therefore no error. That's the declaration, right? If y, on the other hand, is, say, 0, 1, 0, 0, this pattern, it takes these 4 bits and look here, and there is no match. Okay? So therefore, the receipt pattern in this case is not in the code, and therefore declare error. And that's it. Okay? It's not harder than that. Okay. Is this a perfect method? What could go wrong here? Do you see the flaw in the logic here? Yes?
What if the code word is changed to another code word?
Very good, very good. So just because the received pattern is a code word doesn't mean it's actually the code word that was transmitted, right? So suppose that this was transmitted, but the error does it so that we end up here, then the receiver would still say, this looks okay, right? Even though there is an error that has occurred, okay? This error pattern that goes from here to here is an error pattern that we cannot detect. So it's called an undetectable error pattern. Okay. So we will return to that very shortly. But to summarize what I did here, hand waving a little bit, this is error detection for systematic binary. Binary just means that there are bits in, bits out, block codes. So at the input, we have the data, the payload. And since it's systematic, the code word that we transmit will have the information bits at the beginning. And then we have some parity bits, which will be at the end. Okay. So the encoder simply copies the data bits and then calculates the parity bits and put them next to each other. This is transmitted over the channel. The channel adds errors, and let's split them into the errors that belong to the data part and the errors that belongs to the parity part. Okay, we just split them into two parts. And then the receipt pattern y will have one part, which is data plus the errors that occurred in the data part, and then a part which is the parity bits, the transmitted parity bits, and plus the errors that occur in the parity bit part of the code word. Okay, now in the receiver, we split these two, the purple and the green part here. So we take the green here and we take the purple up here. So that's the first step we do. Then the idea here is to take the data part and calculate the corresponding parity bits that belongs to these data. Okay, so basically we have some bit pattern. We look here and we calculate the corresponding parity bits, whatever the received bits happens to be. Okay, and then these parity bits which are here are compared to the parity bits we actually received. If these are the same, then we can conclude that Y is a code word. Okay. Okay, so that's the crucial part. So let's take that once again. So we have some data bits coming in here, and we calculate the parity bits. If these data bits corresponds to the parity bits we actually received, then we can say that the received word is a code word. If they are different, it cannot be a code word. For instance, the simplest case here is when we simply have D as the input here. So we have no errors. And say that we have P here. Then what happens here is exactly what happens at the transmitter side. So the output of the check bit calculation when the input is D is P. All right? And then P is equal to P, so everything is okay. Now, if there is an error here, then in many cases, what we will receive here at the output here will no longer be P, it would be some other vector P, and therefore we detect the error. Okay. Now, what other errors can occur? Well, there could be some errors here. And suppose that there are no errors up here, then the output will be P, but what comes in here would not be P. So we can find errors both in the data part and the parity part. And if there are errors in both, yeah, well, there's little chance that they will be the same. Okay. So the idea at the receiver is to replicate the calculation of the parity bits which is done at the transmitters and check whether the calculated parity bits are equal to the received parity bits. If that is the case, then things are okay, or thought to be okay. If it's not the same, then we for sure know that something bad has happened. Okay. So let's take exactly the same type of code that we have been looking at now for some time, and we say that D is equal to 0, 1. So this means that if D is equal to 0, 1, I know that P is 1, 0. Okay, 0, 1 gives P 1, 0. So P is equal to 1, 0. Okay, which means that the transmitted code is equal to the data bits 0, 1 and the parity bits 1, 0. if the error pattern is such that it's 0, 0, 0, 1, what does that tell us about y, the received bits? Well, it should be the code bits 0, 1, 1, 0 modulo 2 added to 0, 0, 0, 1, which means that we'll flip the last bit. Okay? So the first 3 bits are okay, but the 4th bit will be flipped. What did I say? The last bit should be flipped. Okay, so 0, 1, 1, okay, and here 1. Then at the receiver, we split this into 2 parts, the data part and the parity check part. And then we re-encode the data part to see whether we get the same parity bits as we just received. Okay. So this one gives parity bits what? Well, let's see. 0, 1, 0, 1, it gives 1, 0. Is this the same as what we received? 1, 1. Okay, sorry, it became a little bit messy here. Okay, so what will we declare here? Error or no error? Error, exactly. Because what we received, 1, 1, does not correspond to the parity bits or the data bits we received. And therefore, something must have gone wrong. Okay, so this gives error. Okay, so let's do something else. Let's take another error pattern and let's call it 0, 1, 1, 0 like this. Then the output of the channel Y, what would that be? Well, it will be the input, but the middle 2 bits will be flipped. Okay, so it will be 0, 0, 0, 0. Right? We split this into 2 parts. We take the data, and this gives us the parity check 0, 0. Right? And then we compare this with the received pattern, 0, 0. So what will we declare in this case? No error. Right. Okay. That's bad, right? Because we know, or we constructed the example that this bit, there was errors occurring, right? But we have no way of detecting them. So this means that this is an undetectable error pattern. Okay, so if that happens to happen, then we're screwed. Right? There is no way we can, from the data that we received or the bits that we received, deduce that an error has occurred. Okay. What else could be undetectable? Okay, I will just list all the patterns here that are undetectable. We know this one is, right? It turns out that this pattern is also undetectable. And can you guess the third one? Exactly, very good. And that's it. There are only 3. In general, for an NK linear block code. Okay, this issue about linear, don't worry about that. It's a technical constraint. Most of the codes we use are linear. I won't tell you exactly what that means. It's not important at this stage. Okay. For this case, then there are 2 to something non-zero error pattern. Okay, so let me ask you here, what should it be here? How many error patterns do we have? Or let me do this. How many error patterns are there in possible that are non-zero? So the error pattern has n bits. So the total number of possible error patterns are 2 to the power of n. One of them is 0. Okay. So these are the number of non-zero error patterns that could occur that we would like to detect. How many of these do you think are undetectable? It's super hard to guess, right? But I'll just tell you. It's 2 to the power of k minus 1 are undetectable. Okay. And let me just quickly try to motivate this. So suppose we transmit a code word, and let's call it C0. Okay. There are 2 to the power of k other code, 2 to the power of k possible code words, right? So then we have C1, we have C2, blah, 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 down to C to the 2 or the power of k minus 1. Okay. So here we have 1, 2, 3, 2 to the power of k minus 1 other code words. And every error pattern that goes from, if we transmit this one, then any error pattern that goes like this, and all of these are unique, will not be able to be detected because it goes from one code word to another. But then there is a bunch of other patterns here to other vectors, you know, many of those. How many do we have in total? Well, we'll just continue to enumerate these. 2 to the power of k, blah, 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 up to the last one here, which is 2 to the power of n minus 1, because one of these patterns will go back to the all zero pattern. Right? So we have 2 to the power of n minus 1 possible non-zero error patterns. Out of those, the red ones are the problematic ones because they go to another code word. And these are 2 to the power of k minus 1 in total. It's a little bit quick, but did you get the gist of it? Right? Okay. So of course, when designing a code here, it seems like if we make k small compared to n, then this becomes a very small part of the possible error patterns, and then we must be very unlucky to encounter a non-detectable error pattern. So if we make n 12,000 and k 32 or something like that, then there is a very many error patterns that we can detect and very few that we can't in comparison. Okay. Time flies on a Friday afternoon, so let's continue to talk a little bit more about how to select good codes. Let's talk about Hamming weight and Hamming distance. Have you heard of these before? Nah, It's not rocket science, but the Hamming weight is the number of ones in a binary vector. Okay, so Hamming weight is denoted by W for weight and H for Hamming, and the Hamming weight of a binary vector U is the number of ones in U. Okay, so the Hamming weight of 1, 0, 0, 1, okay, like this, is equal to 2. Okay, it was a bad example because it has as many zeros as ones, but there's the number of ones that we calculate, right? Okay, if we have a weight or a length, we can calculate the distance. And the distance between two binary vectors, the Hamming distance, is the number of it's the number of different bit positions, or rather, the number of positions. It's the number of places when the vectors are different. Okay, let me put it like this. Okay, so the D for distance, H for Hamming. We have two inputs, U and V. It's the number of bit positions in which U and V differ. Okay, and we can calculate that as the Hamming weight of U modulo 2 added to V. Okay, 0, 1, 1, 0, 1, and 1, 1, 1, 1, 0, like this. So what is the Hamming distance between these two? Well, we simply see that here, if we make modulo 2 addition of this, what do we get? First of all, we get 0 plus 1, that's 1. 1 plus 1 is 0. 1 plus 1 is 0. 0 plus 1 is 1. 1 plus 0 is 1. Okay. So the purple one indicates where the two differs. And if we take the Hamming weight of that, we get 3, which is the number of positions where they differ. Okay. Questions on that? No? Okay, so we'll continue then. So there is a minimum distance of a code, and that's how well these code words are separated in space, in binary space. And that turns out to be important. So let's see why this is important. So there is a minimum distance, and this is the mathematical definition of that. We take two code words, two different code words, and we calculate the Hamming distance of that. We do that for all pairs, and the one which is the smallest, we call that the minimum distance. So in this case, it happens to be that C3 and C2 are the closest ones, and then they are on a Hamming distance of d min from each other. Okay, so we see C2 and C1 is further away than d min, and so is C2 and C4, and C3 and C4 are also further apart. Okay, so that's the minimum distance. If we then have an error pattern E, what can we say about that? Well, okay, so suppose we transmit C2 and then we put E here and then we get Y. Okay, so this is the error pattern if we transmitted C2 and then we get Y. And E then, the error vector, is detectable if Y, which is C plus E, is not in the code. Okay, and there should be that for all possible code words. So if we then put E on all possible code words, we should not end up at some other code word. It's basically what we did before here. So it's nothing new yet. Okay. Now, if we then put this spheres around each of the code words, we see that, and here's the thing. If the Hamming weight of the error is less than the minimum distance, whatever code word we transmit, we cannot go outside the corresponding sphere. Right? And if we cannot go outside the corresponding sphere, we can never reach. Okay, so suppose you have to look at this. There is a strict inequality here, meaning that the number of bit errors here is such that we are just inside the sphere. And if we just inside the sphere, we can never reach another code word. Okay. So all error patterns which has a weight which is less than the minimum distance, these are detectable. Okay. Why is this important? Well, it's important because on a channel which is well designed, it's more likely that we have few bit errors than many bit errors. So if the code is designed to catch all error patterns with relatively low weight, few errors, then we will catch a big part of the probable error patterns that occur. Now, these are all the possible ones, but not all of them are equally likely in general, in the normal case. Okay. If the Hamming weight, however, is larger than the minimum distance, then E might be undetectable, but not necessarily, right? In this case, there is only one error pattern which is problematic when it has Hamming weight d-min, and that's this one. Okay. All other error patterns of distance d-min would not be problematic, because then we would simply not end up in another code word. Okay. So this one is problematic, the rest one is are not. Okay. But anyways, this gives some guarantees. Okay. And that's a design criteria for block codes. We would like to separate the code words as much as possible. Okay. Error correction. Not okay. I think we're going to skip error correction here. I will very quickly say something about that. Basically, it's like this, that if we do a minimum distance receiver, suppose we transmitted C2 and we have an error and then we get Y, and we decode to the closest code word, we see that we can correct all errors which are inside this sphere. Right? Because all points which are inside the sphere is closer to C2 than to any others. Okay, so another way, if the weight of the error pattern, okay, so what is the radius of this sphere? Well, it's half the minimum distance. The radius of this sphere is half the minimum distance. So as long as the weight of the error is less than half the minimum distance, then we can correct this error by simply decoding to the closest code word. Okay. So this is error correction, while earlier we did error detection. In real systems, there is usually a combination of these two things, where error correction is taken care of by the physical layer, and error detection is taken care of by the data link layer. So there is two levels of protection here. So in Wi-Fi, for instance, when we transmit bits over Wi-Fi, the physical layer takes care of some of the errors, hopefully all of them, but those errors that slip through the physical layer is caught by the MAC layer, the data link layer. Hopefully, if they are not undetectable, right? So there is nothing perfect in this world. Okay, so I will just leave it at that, and then go on to some of special codes which are used in practice. So now we talked about block codes a little bit, quite generic, right? There are some K bits in and bits out. But how do we do this in practice, and what is important for us? Well, important is, of course, performance, but what else is important than performance? Why don't we all have Ferraris? cost, right? Performance, cost. There's always this trade-off, right? So what are we willing to pay? Okay, and the performance we need is of course different depending on what type of channel we have. I mean, we don't need a Ferrari error detection code if there are very few errors here. Then we can go with something cheaper. If there are many errors here, well, maybe we need a more powerful code and therefore a more expensive code. Expensive in what? Power consumption, hardware, software complexity, and things like that, right? Resources in general. Okay. So, the simplest code we can think of is a code which just adds a single check bit, a parity bit. And this is called single parity check codes. How this is done is that we calculate one check bit regardless of how many data bits we have. And how do we do that? By just modulo 2 add all the information bits here. Okay, and the result is then that the parity bit is 1 if the number of ones in the data is odd, and 0 if it's even. Okay, that's just the way, it's a consequence of this calculation. And then the code word, what is the code word? Well, the code word consists of the data bits plus the parity bit. And if one think about it, this will always, the first part will be just the parity bit. So it will be parity bit plus the parity bit, which is equal to 0. Meaning that the code words always have an even number of ones in them. So what the receiver needs to do is simply to calculate, to count how many bits, how many 1 bits are there. Is that even or odd? That's what it needs to do. Very, very simple calculation, very simple hardware, cheap, right? Is it any good? Well, it's okay, right? But we could do better. But it's not super bad as one might think. The minimum distance is 2. Okay, we go from one even pattern to another even pattern. We need to change 2 bits, right? If we change from an even number of ones, if we change one of the bits in that pattern, we get an odd number of ones. Okay, so minimum distance is 2, so all single bit errors can be detected, for sure. But we can also detect half of all the error patterns, namely those with odd weight. Okay, so 1 bit error, 3 bit errors, 5 bit errors, 7 bit errors, and so forth, because all of these will make the resulting received code word, received word having an odd number of bits. Okay, so this is was used in the beginning when hardware and software was very expensive. It's still used for very reliable systems, for instance, memory storage and things like this, where there's few errors. So actually, you write down your bit pattern, you read it up, and you make a rudimentary check whether what you read is actually what could have been written. Right? Okay, so it's still used in those cases. Okay, any questions on this? So let's go to a little bit more advanced one, which is called the internet checksum. So the internet checksums is used for error detection in TCP, UDP, and IPv4, and it's used to error check the headers. So it's actually not caught by the data link layers. It's called, I mean, you know, IP is on the network layer, and UDP and TCP is on the transport layer. So this is error detection on higher layers, I would say. Okay, so it works on blocks of bits of any length k. So it could be 12,000 bits or 44 bits or 1 billion bits. It works for all of these. And the procedure is following 3 steps here. First, we split the data into 2-byte or 16-bit blocks. If that doesn't add up to the number of bits that we have, we just add zeros at the end so that we get an even number of bytes. So we split the payload into a number of blocks, L in this case. And then we simply add these blocks. We think of this as a 16-bit integer, this as a 16-bit integer, and so forth. And we just add them. And we add them using not the regular two complement addition, but one's complement addition. So if you're not familiar with this, I will show you what that is on the next slide. And this is denoted by plus, and then there is this apostrophe here. So plus tick. Okay, and then the 16 parity bits, so there are 16 parity bits, meaning that this is equal to n minus k, 16 parity bits. No, it's not. Yes, it is. Okay. And we get that by adding all the data blocks, one's complement, and then we modulo 2 addition with FFF. This is in hexadecimal notation, so it's 16 1-bits. So basically, whatever bit pattern we get here, we flip those bits by doing this last step here. And then it turns out that the code word, resulting code word, which is the payload plus the parity bits, if we would repeat this 1 to 3, we would get an internet checksum which is 0. And this is used at the receiver to check whether this is an OK code word or not. Okay. So one's complements addition. So what do we do then? We know that if we take two n-bit patterns and add them together, we might get a n-bit plus 1, n plus 1 bit result. Right? But we want to keep 16 bits. So even if we take 16 plus 16 bits, we might get 17 bits, but we still want the result to be 16 bits. So we can do this with this one's complement addition. So it's similar to addition of n-bit integers. And if we do that in terms of decimal numbers, we have a and b are the two decimal numbers corresponding to the bit patterns, and it's a plus b. The result is a plus b if a plus b will fit into an n-bit pattern. If a plus b will not fit into n bits, we have to subtract off something to make it fit into 16 bits. Okay, so maybe an example would be illustrating here. So we have 8-bit integers here now. So 225 and 155. So in decimal form, it's E1 in hexadecimal, or this is in binary form. So these are three representations of the same number. If we do it in decimal form, we take 255 plus 155, we get 380, which is more than 2 to the n minus 1 is 255 in this case. Okay. Since the result is greater than 255, we subtract off 255, and then we get 125, and this will fit into 8 bits. It's easier to see this in binary form, so we take these two binary things, add them together, and then we get this bit that goes over to the left outside. So we have now 9 bits, and we put that down here, and we add that, and then this result will be the 16 bits. And it turns out that these bit patterns is exactly the same bit. If we calculate it in decimal form, we get 125. If you prefer to do this in hex, we do it like this instead. So 1 plus b is c, e plus 9 is 17 in hexadecimal form. So this 1 we put down here, and we add it together, we get 7d. And this is also the same. I mean, all these numbers underlined with blue is the same. Okay, so it's just a way to do this. So either you program this, or you have a calculator that does this for you, or you do this one of these simple tricks here. Any questions? Okay. So then a simple example of this. Suppose that this is the payload. Okay, so we have a payload here. The first thing we do is to split the payload into 3 blocks, each of them consisting of 16 bits. So we have the red block, the blue one, and the green one. We write them in hexadecimal form here because it's easier to write it down. So 46AA are the red bits here. AE01 is the blue ones, and the green ones are the green ones. Then we just add them. as regular integers, and then we get 1, 9c, 5f. If we just go through this, you have to trust me on this, I guess. And then we have to wrap around the carry bit, and then if we do that, we take 9c, 5f and add 001 to that, and then we get 9c, 60. You have to trust me on that again. Okay, and then to find the parity bits, we flip the bits that corresponds to this 9c60, and then we get 639f. Okay, and now we have calculated the parity bits, and we put the parity bits at the end of the data bits, and this is our code word. At the receiver, if everything is okay, this is also what we receive, and the receiver does exactly the same procedure as we've done here. We add them together, and then we add this red, the blue, green, and this, what should we call it, orange, I guess. We add them together, and then we get 1 plus FFFE. We wrap around the carry, and then we get FFFF. We negate them, and then we get 0. Okay, so this means no error. If equal to non-zero, then declare error. Okay, so this is just the calculations which are done at the receiving end. Now this internet checksum was specified back in the day where computations were expensive. So it was done to tailor-made to particular hardware that could do this very efficiently. Nowadays, that's not the motivation, so now we just use it because of tradition, I guess, or it's been around for such a long time. So this is clearly better than the parity check code, but we can still do better. So if we want to do better, we use cyclic redundancy check codes, or CRCs as they are known. I wonder if we should just call it a day now, and just try to recap what we have done today, and then we'll take CRCs on Monday. So we did the physical layer. We know that there is a trade-off between spectral efficiency and power efficiency, and the SNR determines how many bit errors we get, the bit error probability. So if the physical layer introduces errors, we would like to somehow control that. There are two ways to do that. At the receiving end, we can try to find and correct the errors. That's called error correction. This is typically done, but not always. On the data link layer, we would like to do error detection in order to request a retransmission of the data, or if we don't want to request a retransmission, we can at least throw away the data because we know it's corrupt. So we don't have to bother the upper layers with something which is bad information. Right? So these are two principles we can do. In data correction, data detection, in its core is to figure out at the receiver whether the received bits are is in the code or not, if it's a code word or not. That's the thing. Right? It's the only thing that we need to do. And we know that if we follow this principle that we accept everything which is a code word and we reject everything which is not a code word, we will when we reject the bits, we always are sure that there are errors in it. When we accept the bits, sometimes we make a mistake. And we make a mistake when the error patterns are undetectable. Okay. So it's not perfect. And we would like, of course, the probability for doing undetected or to accept an erroneous payload as little as possible. So therefore, we design these error detection codes. Simplest one is single parity check, cheap, not very high performance. A little bit better is the internet checksum. And then on Monday, we will see the main workhorse in this field, which is called cyclically redundancy check codes, which are used on Ethernet, for instance, these CRCs, and also used in Wi-Fi. Okay. But we'll take that on Monday, so hopefully I'll see you then. Have a nice weekend.